The presented paper is on decoding complex geometry for craftsmanship. Firstly, a little about us. We are CraftQuest, an architectural firm based in Ahmedabad, India. We design and build spaces by integrating technology and crafts. The paper aims to bring forward two important aspects. First, the design to production of shell structures as a close collaboration between the architect, engineer, and craftsperson. Second, to discuss the various opportunities of evolving construction crafts with the advancements in technology. The project in discussion is a stud farm that houses animals in large semi-open enclosures. The layout of the stable is guided around the horse rink, which is at the center. The stable roof was designed as an undulating free-form grid shell spanning over 1,000 square meters. Each stable was required to cover a large span to accommodate the horses. Hence, minimum supports and lightweight shell structure was a suitable consideration. The scope of this paper is to demonstrate through the viewer's pavilion the construction of a lightweight scaffolding-less free-form steel grid shell. A multitude of methods have been used over time to determine precise shapes in equilibrium either through physical models or computational modeling tools, which began quantifying the three-dimensional forces acting on the structure, thus providing real-time responses to the shape of the shell. This translation to the digital space established a high-level control through thrust network analysis. This follows the previous studies done by the first author with the prior example focusing on funicular structures and temporal walls, followed by the development of topological modules with limited customization and motorless construction. The workflow illustrates the stepwise process from design to construction. The various stages in which the structural engineer and the craftsman have been closely involved have also been illustrated in the left. The form finding process, material selection, introducing the master craftsman to the design process, followed by further iterations in form. This was followed by structural analysis and structural optimization, revising the structural grid and devising the construction logic in various stages. Finally, finishing with architectural details. The following three parameters for form finding were to minimize the number of supports, maximize view, and restrict the peak height to 4.5 meters. The first set of iterations were generated with varying support conditions, beginning with linear supports and ending with 5-point supports. From these iterations, it was clear that the room was best suited with a 4-point vault. From these inferences, the base surface was divided in two, one for the 4-point vault and the other for the 3-point support shell. However, the 3-point shell induced an acentric load, resulting in the structure being unstable. Hence, the support located in the periphery was brought to the center, making it a tripod support in place of the longer cantilever. This led to iteration 3 with the introduction of the teardrop column to be able to distribute the loads equally. As indicated previously, design generation began with the idea of a funicular shell being constructed using clay tile and cement mortar in temporal vault technique. The other option was the potential to test the ongoing research in limiting the customization of topological assemblies in constructing funicular walls and freeform shells. Towards the end of the form finding stage, the design brief was updated. The structure was required to be temporary in nature, hence the need of thinking of an alternative material occurred. At this point, the selection of material was dependent on the cost of the material and the availability of craftsmanship. Based on these criteria, steel and ferrocement was chosen, thus changing the behavior from membrane to grid shell. Following the form finding process, the rectilinear grid of the 3-point shell was revised to a diagonal grid along the lines of forces passing through the teardrop column, thus ensuring structural stability. Dead loads, including the self-weight of the members, ferrocement, and live load were considered. Analysis showed a maximum deflection of 60 mm. This was in the permissible range. Additionally, this value is expected to reduce due to the stiffening from ferrocement in reality. It was then proposed that additional bracing members be added to support the structure. The structural members were optimized and the layers of construction were fixed in the stage. The bent pipes were overlaid in both directions of the grid shell, hence forming overlapping junctions that were required to be permanently welded after mounting. 8 mm thick base plates were used to anchor the superstructure to the plinth. It was established that construction without scaffolding would save costs to a large extent. Hence, this became the basis for defining fabrication and assembly logic. The construction began with a 4-point vault due to its simplicity in construction logic. It was used to train the craftsmen and ensure their seamless transition from single curve bending to double curve bending at a later stage. The scale model was used to understand the fabrication technique that would be employed on site. It was clearer from the prototype that each member of the regular grid would be bent in a plane that passes through the two endpoints and a point of maximum peak. This logic was determined for the fabrication drawings and subsequent construction. The logic from the scaled model was used to generate the fabrication drawings for the freeform shell. The boundary and the bracing members were mounted first, followed by the first layer in the U direction and then the second layer of members in the V direction. The midpoint of each member was cross-checked with the help of a jig at critical points. On completion of the grid shell, the joints were permanently welded. A total of 6 layers of chicken mesh were affixed above and below the completed grid shell. Ferrocement made in cement and fine aggregate ratio of 1:2 was then applied manually. A second layer of ferrocement mixed with a 4% brick pigment was then applied to the outer and inner surface of the shell. Design intention, type of shell, and material selection influence the initial choice of software to be used in design. It is when these tools are used in conjunction with the expertise of craftsmen who have acquired knowledge over time that the project becomes more rooted to its context. Contemporary design practices like craft-based Ibuku are good examples of this amalgamation. It was found through comparative analysis that for the shell, the total weight of steel reinforcement bars was higher than the total weight of pipes of the same diameter proposed. This resulted in significantly reducing the material used and hence the overall weight of the structure. Close collaboration among architects, engineers, and craftsmen can help bring their respective expertise to the table while also exchanging ideas that can bring about novel forms of construction. There's a limitation of manual bending as one can bend a maximum of 48.3 mm outer layer, 4 mm thick MS pipe. These constraints of craftsmanship shall be used as design parameters while upscaling. Handling manual pipe bending drawings was cumbersome for craftsmen on site. Hence, training the craftsmen for mixed reality tools like Hologram would help simplify the translation of the design from digital to physical space by extending their capacity to visualize the shell in real time. Thank you.